Welcome to Mrs. Mahoney's podcast. This is our first one on Unit 11, not Unit 10 like it says in your packet, so make sure you change that. We're in Chapter 19 in our book. You had the bookwork, and now we're just going to talk a little bit more about what you covered, you should have read when you first started reading this. So acids and bases. Let's go with some of the properties. So on the top of page 2 here, it's just some general properties of acids. First thing, they have a sour taste. Now these two other comments, you don't have to write that, but just some things to know. But you would never in the lab use that as a taste. But you have taste acids. Lemons, citric acid. If you've ever had those Sour Patch Kids, ascorbic acid, read the back of the labels. Anytime you eat something sour, stomach acid. When you get sick, that's sour taste because of the acid in your stomach. Number 2, they can change the color of acid-base indicators. Litmus paper, and like it says in the color of the book on the front. Expect that you, I've seen where it shows up that you know that litmus change bases blue and acids reds. And litmus paper is just a type of an indicator. And we're going to talk more about indicators when we look specifically at the neutralization reactions. A third one, they react with metals to release the hydrogen gas. There's an example. Again, I'm giving you an example. This is a single replacement reaction. And again, not all metals will do this, but many of the metals will have this reaction. All acids will react with the bases to produce salts and water. Probably want to put this is called a neutralization reaction. Again, we'll spend more time on these as we get going towards the end, and then we'll do some titrations and some calculations for neutralization reactions. And again, this is a example, acid with a base, and you get a salt and water. Now salt does not just mean sodium chloride. Salt is actually an ionic compound that comes from an acid-base reaction. Just salt is one, table salt, NaCl, is just one type. And the last one, they can conduct electricity, and some conduct better than others, and we're going to talk about what makes it weak and strong. And what happens, so this is where it's an acid that we'd say it's covalently bonded, but it creates the ion. So we say that it's ionized, creating ions, but just like an electrolyte, you have to have ions in order for it to charge or to conduct electricity. Okay, acids. You've named acids. And we know that with an acids it has to have this hydrogen. We said compounds that begin with the hydrogen. So that's the ions we're talking about when it we say it ionizes. So what happens, this hydrogen ion is going to attach to a water, and this is called the hydronium ion. You just need to know that this hydronium ion is used interchangeably. Sometimes we'll just talk about the hydrogen ion. Now these brackets are going to mean concentrations, and we'll start talking about that. But hydronium ion, the hydrogen ion, they're going to be used interchangeably. You need to understand that they mean the same thing, and they are being produced from an acid. Okay, so Arrhenius is the first definition, and his was the traditional. What you look at when you say if it's a compound aqueous solution that has that hydrogen, then it's producing that hydrogen. That's what makes it an acid. And that's still how you can recognize if it's an acid, you're looking for that hydrogen. Okay, Bronsted-Lowry is a little bit broader because they said, well, wait a minute, not all compounds necessarily fit that definition. So I went a little bit broader, and he said it's a proton donor, and this is Bronsted-Lowry. Now, a proton donor, but the thing is the proton is the form of just H+. This is what a proton is. It's the hydrogen with the +1 charge. That is a proton. So really, if you look, Arrhenius and Bronsted-Lowry, not that big of a difference between the definitions. The bases are where we can see a little bit difference. Okay, the acid strengths we're going to talk about. Is it a strong acid? Is it a weak acid? Wish it was really easy if you say, okay, H3PO4 phosphoric acid has 3 hydrogens, therefore it must be a really, really strong acid. doesn't work like that. It's all about how many ions. So the strength, and you definitely need to know this definition. I haven't put that there. I would add this, that the strength of an acid and a base, so it's the same thing, is how much it ionizes or separates into the ions. Ionic compound for a base is, so it's really how many ions. The more ions, the stronger we will classify it. So I gave you some examples written here, and so this is what you're looking at. And notice right now we're going to start noticing some difference. This is going to a single arrow saying it's going to completion. This is saying that it's nearly all of this is being disassociated and it's making all of these ions. Compared to the weak, notice the weak. This is a reversible. And so what it means is that I have this hydrofluoric is breaking down into the hydrogen. And again, notice I put it as a hydronium. Sometimes you'll also see it being broken down just like this, recognizing they're doing the same thing. But at the same time, these guys are getting back together to make the acid itself. So you have both of these going on, and in fact, you don't have very many ions being produced. This might light up a light bulb, but it's going to light up really, really dim. That's our definition. Now on the page 2, I've given you the actual names of your acids, of your strongs and weaks. And just a heads up, if you're going into AP, you will need to know the strong acids and the strong bases, as long as the weaks. And really we'll realize that you only have about 7 or 8 strong acids and the rest are weak, and you just easiest to know the strongs. But we'll notice the difference. It's making this hydrogen. That's what makes it an acid, makes the hydronium. So how do I know if it's an acid? You're looking for the hydrogen. Okay, then how do I know if it's a base? Okay, let's look at some of the properties of a base. And I would put right here, first thing, just to get the most easiest, there we go, the easiest, the most common thing you are looking for, we'll look at a few of the definitions, is that OH. That if it's a compound with, so therefore a hydroxide is a base. Okay, here's some properties. Aqueous solutions taste bitter. Think of soap. If you've ever gotten soap or shampoo in your mouth, you've tasted bases, and you know that bitter taste. They also can change colors of indicators. So again, that was why you knew the color of the litmus paper, and again, it's on the cartoon in the front. And that really wasn't anything funny, just kind of had some actually good properties of acids and bases. Maybe if you keep reading them, they'll stick in your head. A third thing, they feel slippery. Same thing, think of soap and shampoo. Definitely you know that they're slippery. When we start doing some titrations, if you have some dilute base, you get it on your hand, you'll definitely can feel that slippery feel. They react with acids to produce a salt and a water. Same thing, this is that neutralization reaction again. So you're going to see definitely some common between acids and bases. So this was that neutralization reaction. And then the last one, again, they can conduct electrical current, and again, some stronger than others. This is all about their solubility rules. And so if it is soluble, then you're going to get more ions. Those on the slightly soluble or insoluble, you're not going to get nearly the ions, and we're going to classify the same thing, weak or strong. So let's look again at the definitions then by the two different names. So with Arrhenius, and again, this is still for right now the easiest you're going to see. We will look at a few, and then again next year AP will look at a lot more that definitely of the weaks that aren't the traditional the hydroxides, but the majority of what you're going to see, are these hydroxide compounds. And so if it increases that hydroxide concentration, that was the definition. Well, Bronsted-Lowry again said, okay, let's make it a little bit broader. And so what it's going to be is the proton acceptor. Again, what's the proton? Is that hydrogen acceptor. And I'm going to show you some definitions. We're going to go through and hopefully to make these definitions make a little bit more sense of what I'm talking about when I'm saying it's donating or accepting a proton. We're going to see some examples of what that looks like so you can identify it. Most common one I would add at this right now is ammonia. Ammonia is a base. So this is one of the biggest things. So if you look at by Arrhenius's definition, just kind of looking at it, you wouldn't automatically classify ammonia as a base. It is a base. And if you think about a lot of your cleaners, most of your cleaners have that ammonia in it. And again, that slippery and those properties shows that ammonia is also a base. Same definition as strong and weak. Notice, a strong, you produce a lot of ions. There's a lot of ions. This is really going to shine the light bulb really brightly. Again, single arrow meaning it's going to completion. It's totally separating. Weak, right here, it's going reverse. Again, here's that ammonia. So what's happening, and so look at right here what's happening. How did I go from NH3 to NH4? It gained an H plus. So we say it gained an H plus. That is the Bronsted-Lowry's definition of what makes it a base. But look at also what it produced then from water. How did it gain it? It stole it from water, and that increased that hydroxide. That's also where you're seeing that it's got the properties very similar to the base. It's just how did it get it? It didn't just ionize it. It didn't separate into it. It actually stole it from water. Okay, so let's kind of look then what's going to happen. And here's a word I would kind of add over to the side. You have some on page 3 where we're going to go through, so you have some equations that kind of look like this. I would write down just some of this definition of conjugate acid base. They're just partners. So if I have an acid, what its partner is going to be we call a conjugate base. If you have a base, this partners is going to be a conjugate acid. Okay, when we're looking at these, notice what I'm looking for here. I'm talking about weak acid and bases. So we're looking at these reversible reactions. These are not neutralization reactions that I'm looking at. This is like what happens with that acid and base in the water, and just looking at the reaction that happens there. So the conjugate base is what's formed when an acid loses the proton. The conjugate acid is what forms when a base gains the proton. But the big difference when you're looking at the partner, saying what is its partner, it's just that one proton. And again, we're going to show the definition to say where's that one proton. So let's look at some of these. So in your packet, kind of do these together of what some of the definitions. So let's look at this first one. I have sodium hydroxide, just breaking apart into sodium and hydroxide. This is a base. And this would be our Arrhenius base, because what's just happening is it's increasing the hydroxide. It's just splitting apart. This is your traditional definition of a base. Okay, let's look at what's going on here. So I have H2, this is carbonic acid. That should help with the name, in water. So look at what's happening over here. I have HCO3 and H3O plus. When you're looking at what's the difference, again, the only difference, all that can be different is one hydrogen. So how did I go from here to here? What is the difference? How did I go from H2CO3 to HCO3? This lost one hydrogen. It lost an H plus, so that's why it's now negative, because it lost a plus. So this means it's an acid, because remember the definitions. You may want to add yourself a note. Acids lose the hydrogens. Bases, and it's an H plus, gain this H plus. We're transferring. That's what's going on in these. We're just transferring. So what did water do? Look at water. How did I go from H2O? So what's the difference? This has 2 hydrogens. This has 3. It gained, therefore it's a base. Now look at its partners. What did we just say? We said the partner of an acid is a conjugate base. Partner of a base is a conjugate acid. You can write it all out if you want to see conjugate. What was that word again? Conjugate base. I'll write it the first time. Conjugate acid. Partners. Okay, so look at this. NH3, find the partner on the other side of the equation that only has the difference of one hydrogen. So NH3 to NH4, how did it do that? It gained, so that means NH3 is a base. So therefore, water has to be an acid. You can only have one acid and one base on each side. So if NH3 is the base, that means NH4 is the conjugate acid. If water is the acid, that means hydroxide is the conjugate base. And what's your double check? Go in reverse. Because look at, how did I go from OH to H2O? What happened there? It gained. What gains? Bases gain. So that's why it's a partner, because in the reverse direction it's doing the opposite. So I'm going to leave this one for you. You can try that one, and we'll start with that. Also, I want you to practice on your reviewing your names. Find your naming and go back through how to name. We did that on the Dana Center. So I want you to finish the rest of page 3, and that's where we're going to kind of start tomorrow when we're looking at everything. I will see you tomorrow.